All right, so we are here to discuss the topic of conservation of energy. We have discussed a little bit about this in class with the fact that, wow, I cannot spell energy apparently. I want to spell earth. Okay, energy. Uh, we've talked about it in class that the energy that we have can be transformed into many different types of energy. We talked about how we have kinetic energy, which has the equation of 1/2 times the mass times velocity squared. The more the mass, the more the kinetic energy, and in fact, the more the velocity, the more the kinetic energy. And it actually obeys a squared type of property. We also have stored energies, so we have a potential energy, and this potential energy is gravitational, or it can be gravitational, and the equation for this is mass times gravity times height. And then we can also have potential energy stored in a spring, which has the equation of 1/2 times the spring constant k times x squared. So let's see if we can use these equations to take a look at a specific situation. And that situation is going to be one where we have a book. Okay, here is our book. That book happens to be 3 kilograms in mass, and it is above the floor. There's the floor, and there is a total of 2 meters between the book and the floor. So it's 2 meters up in the air. Someone's holding it. Okay, and then you let it go, and the book is going to come all the way down here, and it's going to smack against the floor. Okay, so our question is, what is the velocity, what is the speed of the object right before it hits the floor? Okay, now we can solve this using kinematics, right? We know that it's 2 meters off the ground. We know that it falls with a gravitational acceleration of g, which is 9.8, and we can solve that using kinematics. So I'm going to show you a different way that we can solve it. We can solve it using energy. So we know that there is a certain amount of energy that this object has because it is 2 meters above the floor. And the question is, what kind of energy is it? Well, it's not moving, so therefore it has to be stored energy. And we're not talking about anything involving a spring, so it's actually this one right here. It is the gravitational potential energy. So it has some potential energy up here, and we can solve for what that is. It's mass times gravity times height. If you do the math, it would be 3 kilograms times 9.8 meters per second squared times a 2-meter height. And that gives you, if you put it all into your calculator, gives you 58.8 joules of energy. Okay? Well, when you drop the book starts to pick up speed. So now it's picking up kinetic energy, but it's losing height. So as it falls, we know that it is increasing in speed, so it's increasing in kinetic energy. Kinetic energy is increasing. But because it is falling, we also know that potential energy is decreasing. Okay, so the question is, okay, what is the potential energy right before it hits the floor? Well, we can solve for it. It's mg times h, but in this case, h would be 0. So how much potential energy do we have? Well, we don't have any. No potential energy. So therefore, it all has to be kinetic. It all has to be kinetic energy. But according to conservation of energy, we know that energy cannot be created or destroyed. So therefore, all of the energy that we had in potential must have been converted into kinetic. So we know that the kinetic energy down here has to be equal to 58.8 joules. Okay, well, 58.8 joules, we know that is also equal to 1/2 mv squared. So we come over here and say, okay, well, kinetic energy has to be equal to 58.8 joules, and that is 1/2 times mass times velocity squared equals 58.8. And our job now is to solve for velocity. So you can multiply by 2 to get it to the other side, and I can also divide by this m. So v squared is going to be equal to 2 over m, because you multiply by 2 and then divide by m times this 58.8 joules. Okay, now we know the mass is 3 kilograms. We can plug that here in a second, but we have the square to worry about. So we know that what we're going to have to do is square root. Okay, so square rooting this gives us that a velocity. If you did all the calculation, it would give you 6.26 meters per second. And that would be the velocity. And I guarantee you that if you solve this using kinematics, then you would come out to have the exact same information. Okay, so this is a simple kinetic or potential energy being converted into kinetic energy. So what if we took a look at it halfway down? What if the book was now only 1 meter off the floor, but it was moving with some velocity? So how fast is it going when it's halfway down? Well, you might have the urge to say, well, it's going to be half this velocity. If it's halfway down, it's halfway the velocity. But you want to make sure to remember that the kinetic energy formula depends on v squared. So if we take a look at this situation, I'm going to redraw it. We take a look at this situation. We have the book was 2 meters above the ground, but now it is 1 meter above the ground because it has fallen, and there is the floor. So it has some velocity going down, and it is currently 1 meter above the floor. Okay, so it started off at 2. Well, we know that the potential energy up here was 58.8 joules. We also know that the kinetic energy down here was 58.8 joules. So what about energy here? What kind of energy does this book have at this point? Well, it still has potential energy because it is high above the ground. It's 1 meter high off the ground, so it has still gravitational potential energy, but it's moving, so it also has kinetic energy. Okay, but we know that it can't have any more than the initial energy that was originally in the system. So it has to have 58.8 joules total energy, and that is going to be the potential energy plus the kinetic. So if we did that, then it's going to be mass times gravity times height when you're halfway off the ground plus the kinetic energy when you're halfway off the ground has to be equal to 58.8 joules. Okay, well, if we're looking for the velocity, how fast is it going, then we're interested in the kinetic energy because that is 1/2 mass times velocity squared. We're going to subtract this mgh to the other side and gives us 58. Okay, try that again. It gives us 58.8 joules, subtracting the mass times gravity times height, so 3 kilograms times 9.8 times 1 meter. All right, and we're still looking for velocity, so that is giving us 1/2 times 3 times velocity squared. This is 3 kilograms, by the way. Okay, equals this all right here. If you plug that into your calculator, it gives you 29.4 joules. So 58.8 joules minus 29.4 joules actually gives us 29.4 joules. So it's gone halfway down, and it is now half energy, half kinetic energy. Half of it's in potential, half of it's in kinetic because it's gone halfway down. But what does that mean about velocity? So if we continue on, velocity is going to be equal to, you multiply by 2, divide by 3, so it's 2 over 3 times this 29.4 joules. And just like before, we're going to have to square root. Okay, when you plug that into your calculator, what you get is 4.43 meters per second. So notice how this is not half the value it was before. Right? It's not half. And the reason why it's not half is because you had to do this square root. So therefore, it cannot be half. It's probably something around square root 2 or something like that. But you notice that energy is half. It has half the amount of energy that it had previously, 29.4 joules. So energy is being converted as this thing falls. This falls from potential to kinetic, and any point in between has to be equal to the total amount of energy, which was defined at the very beginning. So at any point, if we did it right here, which say is 1.5 meters above the ground, or if we did it right here, which is, say, zero point 0.5 meters above the ground. Both of these situations would have to have a total energy of 58.8 joules. Some of that would be in potential, and some of that would be in kinetic. So this shows how energy can be conserved, and we can utilize the conservation of energy property to help us solve for the velocity of something as it falls.